go here, complex, I have to select whether I want it in that or that.
Oh, you can just straight up put it in.
So like say 2, and then
Peter is online
complex.
How do you put in like complex?
Can you hear me, Peter?
Yes, sir.
See, there's an I right here.
Your teammates are complaining.
Say 2 plus I. The I right there.
Oh.
All right. I hope you're okay, Peter. Feeling good.
It's only an hour.
Yeah,
I'll be okay. Thank you.
and then it actually gives me my answer for that in this.
Yeah, I'm gonna have to figure out if I can put it.
Okay. Two people online today. Julian, can you hear me?
Phaser form.
Can you hear me?
Yeah, I can hear you.
Okay.
I literally just figured all that out.
Yeah, I'm gonna have to mess around with it over the weekend, and that's just to do the homework. And there's a quiz in the exam.
It's not gonna go on.
Oh, he's gone.
What happened to Julian?
What happened? Okay. Oh, he come back. Yeah, we still have time. Looks like 2 people online. I guess a few people missing today's class. Athletic events and also some kind of activity about this.
Oh, let's go, dude. The structured homework is gonna be so much easier. Who needs a MATLAB? We have a calculator.
It's good for you, right?
Doing okay?
I don't know how the hell.
Do you have any question about the exam coming up on Monday?
Everyone talking to us like that.
We have exam on Monday.
What's the answers?
I haven't made up a problem yet, to be honest. I'm going to spend some time over the weekend creating 3 problems, so you can sort of manipulate if you want to.
Do you know what you're doing?
I mean, if you stay quiet, I'm going to create any problem I want to create.
And if you go from B1.
What kind of?
No.
Well, that means, staying quiet means students' statement saying, "Professor, you can test any way you want to." I'll take the challenge anyway. Do you have any questions, comments? Yeah, right. A5.
One from A5.
One from A5, maybe.
It was like the moment of the list.
I think I used your pressure and
That problem,
That's the
huh?
one I always
That's, okay, could be.
Okay.
That was, okay, come up with the equations of this distributed pressure and shear stress over the surface, integrate from leading edge to trailing edge to determine if, you can do that, of course. I mean, did I give you a homework just like that? If not, don't worry about it.
It was more focused on finding locations. We just did that in
We only
class.
did locations.
Okay, could be.
For the homework, yeah.
So again, if I create all of a sudden, like, hey, problem you have never seen in your homework or class example or quiz or anything, you can complain about it, of course. I'm not going to do that.
But will our complaints?
Suppose if I choose a similar, very similar problem, almost cut and paste from homework, and if you screw up, you cannot complain anything about it, of course.
Yeah.
Yeah.
That's what I did on exam 1.
Yeah.
Isn't that right? Okay.
Yeah.
Go ahead.
You said it's only A5 through B2, not B3, right?
Did I say that?
Yeah,
I don't
yeah,
know.
you said
It's-
A5.
It's in
Did
the
I say that? I
announcement.
don't know.
Yeah.
Oh, I forgot to share my desktop, sorry. Let me share the desktop for those online people, okay? So online people, can you see my desktop?
Oh, that's true.
Yeah.
Okay.
Yep.
Okay, so that's it. So this is the announcement. So let me just take the in-class attendance. If I announce one thing and if I do something else, you can, of course.
Again,
Okay.
things accomplish something.
As a professor, we cannot do such a thing. Of course. No one does such a thing.
In that scenario,
Yeah, right.
in that scenario, will our complaints accomplish something?
Well, you can complain always to the dean, you know, I would encourage you to go talk to the dean, that's his job, otherwise he's not gonna do anything.
Are we allowed voters?
Alrighty
I
then.
mean, you have to create the job for the dean.
Alrighty.
Am I recording this?
Well,
Yeah,
it's
that's
made
good.
out of pieces, yeah.
Okay, so again, exam is essentially, my intention is, trying to make sure that you are honestly trying to do every problem, trying to solve it by yourself, not copying from my old solution, copying from your teammate, your classmate, and then have no clue what you're doing, but pretending like you're doing something. That kind of thing shows up on exam, of course, always, okay? So in my own opinion, this is not exam. I'm not challenging at all. If you're doing all the problem all by yourself and comparing your work against my solution, correcting all the errors and understanding what you're doing, this is entertainment, it's not exam. Okay? That's what I say safely, because I don't wanna give you more things than what you have already given. Okay? So again, that's what I'm not. That's why I keep saying just to do one problem solution one at a time. Homework assignments. And then let's just understand. This whole entire semester, the aerodynamics is an elephant. Aerodynamics 1 is elephant. How do you eat elephant?
One bite at a time.
One bite at a time.
You said elephant?
Elephant. How do you eat elephant?
I don't.
One bite at a time.
Yeah.
I mean, didn't your kindergarten teacher say that? How do you eat an elephant? One bite at a time.
I don't know, but I know how to do it.
Fork and knife.
That's the only way you can eat such a thing. Okay? Do not try to eat everything a night before, then you probably need to rush into the restroom in the morning and spits out everything out. And then you have all of a sudden, oh, my mind went all blank white. Of course, because it spits out everything before the exam starts to happen. That's what happens. If you eat one bite at a time, everything is all yours. You actually kind of look at the problem, how rough is that? I know this. Okay? All right. So don't worry about it, but please do whatever you're supposed to be doing. Engineering is all about that. It's not like passing this class, just memorizing and, forget everything a day before. And that's not the study at all. It's not engineering. People like that just graduate, get a real job. You know what they do? You know what they do. They make mistakes. Somebody get hurt, people may die. Okay, that's what happens always. Okay, so again, let's do engineering. Okay. All right, so anyways, so where did I stop in last class? I think we looked at, okay, so this is a flow over a circular cylinder without having any circulation in it. So this is non-lifting flow over a circular cylinder. Let me just put the memo here. Sorry, I forgot to connect my drawing tab, sorry. Okay, so this is something called non-lifting flow. Over a cylinder. Why this is non-lifting, by the way? Somebody please tell me a straight answer for that. This one doesn't have a lift at all. Why?
No circulation.
Because no circulation, you're saying? Oh, that's great. Actually, that's very good description of why you don't have a lift. Because you have no circulation in the flow field. There's no mechanism of creating any circulation in a flow field.
Would it also be accurate to say that when you integrate the pressure distribution over the surface, it's equal to 0?
Because the pressure distribution over the surface in certain direction is completely symmetric.
Okay.
Yeah, you can say that too.
Okay.
And then you can say that because we have no circulation, we have such a pressure distribution. Okay. So this is actually a very first fundamental idea of the theory of aerodynamics, circulation theory. Circulation is 0, no lift. you can apply this theory exactly as it is to the flow of a cross-section of a wing. It's called circulation theory of aerodynamics. It's a German origin. Prandtl, Ludwig Prandtl, is the one who actually developed this whole thing. So we are going to refer more and more to his name, and then lots of things called Prandtl's fluid mechanics or fluid mechanics theory developed by Prandtl. So this is Prandtl theory of aerodynamics, very classic theory, in which this country actually accepted right after World War II. Okay. So aerodynamics in this country, the United States, is based on German theory. Okay. Interesting. And then Japanese professors teaching that. Interesting, isn't it? How come you shouldn't say this? No more butt jokes. Okay.
Are there opposing commonly accepted theories for wide lift disc?
Some people actually pick up Newton's impact, like a third law of motion of Newton's impact reaction kind of theory. Occasionally they do. We don't. However, come down to the circulation is about the similar, commonly accepted, theory for like worldwide. So, however, some details will be different. Okay. Again, but we adapt almost as is the Prandtl theory. Okay. So now, remember last class. Okay, we introduced you handout. Okay. Quite important handout. Basically, lots of people probably ignore this handout. I know that. That's why I'm going to tell you right now. This handout contents may all of a sudden show up on final exam. Be ready for it, if so. So this is quite important mathematical details. I want you to go over it. So if there's no flow circulation in the flow field, this is the pressure coefficient distribution over the surface of the non-lifting flow of the circular cylinder. Is that correct? Non-lifting means circulation is zero. Flow over circular cylinder. Then, of course, you went through twice coordinate transformation process. This is the coordinate transformation, streamline coordinate S into the Cartesian coordinate X using coordinate transformation. Okay. Then you come up with CL, lift coefficient equation, which can be given by integration from leading edge to trailing edge of the CP distribution difference between top and bottom surface is going to get you lift. Of course, if you can do CP distribution difference between forward and backward surface, from here to here, from here to there, you can determine the drag. Okay, so this is only a lift coefficient, but you can, of course, compute the drag coefficient also. With the same token, you can determine the pitching moment about where, I don't know, pitching moment at the center of the cylinder, which is half code, is of course zero. Right? You can compute CL, CD, CM at any location along the code. Now, code in this case is of course 2 times radius, right? Sorry. So this is leading edge and trailing edge. This is radius. So the code, I keep saying code C. Code C is equal to 2 times R. This is diameter. Okay. Now you can compare against actual cross-section of a wing. Oftentimes we refer to the leading edge and trailing edge, and then connecting up the straight line. This is called code length, right? This is a code. Code is a code. In this case, code is 2 times radius, because we are using radius as a normalization factor of x. Okay. Okay, Robert, this is not vector. Okay. This is x normalized by r. Why do we do that? So that x is independent of the actual size. Yeah. Okay, good. Do you remember x over bar definition for this case, Robert? What is the definition of x over bar for the cross section of a wing airfoil?
Is it going to be
X by code length.
yes?
Right?
Yeah.
Okay, so it's a quite a bit, actually slightly different definition. Because for the circular cylinder, we normalized x divided by radius, which is 2 times r, which is a chord length. Chord length 2 times r. Now, in case of the airfoil, we normalized using the code, okay? So those are not the exact same thing. One is 2 times radius, right? That's why this 1/2 is in place right here.
Oh.
Well, I said the same thing in last class, but anyways, that's a good response. Oh, yes, 1/2 comes in because we normalized using radius, not the diameter. Okay, be careful about that. That's quite important. So next step is, of course, second time transformation of the coordinate. Now you're going to transform Cartesian x into theta, which is polar coordinate, using this as a transformation equation. Then you are going to integrate from leading edge to trailing edge for upper surface and the lower surface. Theta equal to, this is pi, theta equal to 0, this is 2 pi, right? So you are going to integrate lower surface and upper surface, take a difference between the CP distribution. Now CP distribution is this. This is a function of theta, okay? So you can finish up your integral, go through this mathematical operation, then the result is CL is 0. That's what we did. Okay, so we're going to move on from this page forward. Any questions so far? This is just a mathematical detail, quite important, okay, to compute actually lift coefficient using the distribution of surface pressure, okay? Because when you start using your software, this is exactly what the software does. Okay, software computes the surface pressure CP distribution from leading edge to trailing edge and product. And then next thing is you're going to integrate over upper and lower surface to determine lift coefficient out of it. Okay, this is the exact same process, mathematical details. So moving on to the next page. Okay, so let's just take a close look at the meaning of this CP distribution of the non-lifting flow over the surface of the circular cylinder. So this is, interestingly, sine function, right? This is a pure function of theta, of course. And then you're talking about the CP distribution over the surface. So suppose if you plot theta starting from here, theta equal to 0. This is the theta equal to 0. And then let's trace out what is the CP distribution over the upper surface. Theta 0 all the way to, let's say, pi. Theta equal to 0. Theta equal to pi. This actually traces out the upper surface pressure distribution. So you're looking at right here. So theta equal to 0, CP is 1, right? And then you're going to trace out all the way to pi. Here, yeah. So this is theta equal to pi. So theta equal to pi, you're going to have another CP equal to 1 location. So this is a stagnation point. It's a stagnation point. And then halfway through here, this is theta equal to half pi. CP equal to, oh, looks like minus 3. CP equal to minus 3. At this location, surface velocity is maximum value. 2 times original V infinity incoming. So this is velocity 0 location. Velocity is decrease. Velocity 0. Velocity actually starts increasing. Okay. Velocity 0. Velocity starts increasing at the same time. Pressure goes down and goes down and goes down and down and down. Reaching the minimum pressure point, CP equal to minus 3. Velocity is 2 times V infinity right here. This is maximum acceleration, minimum pressure point established here. And then as you move on and on and on from here, pressure actually increase and increase and increase. What's that? So what do you mean? This is a favorable. This is adverse pressure gradient, right? Which one do you like better? Do you like favorable life or adverse life? Favorable life is probably your freshman semester. Right? Adverse life is after you start taking, like, I don't know.
Aerodynamics.
No, aerodynamics is probably behind the minimum pressure point, I guess.
Yes.
You're already snapped and flow separated and then realized and reattached and let's try to graduate somehow kind of moment, right? Isn't that true? I mean, first encounter of, wait a minute, this is not high school kind of moment. That's probably statics and maybe solid mechanics, fluid mechanics. Oh my goodness, dynamics. And then thermodynamics. Then at that point, some of you basically snap it and probably flow separates from the surface. And then, oh my goodness, I'm going to drop this stupid class. I'm not going to take this class anymore from this stupid professor. Or I'm going to take this from this professor. Whoa, this professor is even worse. That kind of moment. How come you're so quiet? I don't know. Okay, anyways, question, go ahead, question.
Which class that
Question. So your life become more turbulent. So the transition starts to happen, okay? So if the pressure is very favorable, you don't have to transition laminar from laminar. Your life is super smooth. Oh my goodness, your freshman semester. My life is smooth and pressure goes down all the way. I'm cruising, I'm partying, I'm relaxing, taking a break and having fun. And then all of a sudden, starting from like, I don't know, sophomore year, sophomore semester, something like that. Oh my goodness, do I have to study? Oh yes, you have to study. Oh my goodness, well, okay, I don't need to sleep. I just start cutting off my sleeping time. Oh, I don't need to eat. Oh, I don't need to bathe. I don't need to shower. I don't need to do anything. I have to study. Then your life is more like a turbulent, right? That's a transition. Laminar to turbulent flow transition. And then if the pressure is too advanced, you basically snap it and say, I'm going to quit. Oh, give me a break. I'm not going to study anymore. I quit. That's flow separation. Flow separates. And then creating just a temporary vacuum, which is relief of the pressure. That actually, you know, depending on the contour design, the rest of the academic year, that separated flow may be attached on the surface, you know, basically repent and come back to professor saying, hey, can I take your class once again? Sure, of course, if you pay money. Yes. And then you reattach on the surface, then somehow graduate, roll away. So same thing. It's a design of the shape or contour. It's actually trying to control your pressure gradient. Pressure gradient is a shape design. So that's the motivation of you how to design your cross section of an airplane, right? So I think I'm saying the same thing over and over. I think Stephen knows. Okay, so I'm actually designing pressure gradient, not the shape. I'm trying to control the behavior of the flow. That's the whole purpose of using that stupid software XY5, trying to shape it. So that shape is going to control the pressure gradient, and it is going to ultimately control the behavior of the flow, so that airplane may or may not, you know, meet your goal of your performance. That's the whole idea. Okay. So, anyways, let's just move on. Take a look at. So this is the pressure change. Stagnation point, minimum pressure. So if you take a look at bottom side, the bottom side is theta equal to pi, all the way to 2 pi, isn't it? All the way to 2 pi. So this is the bottom surface. So theta equal to pi, right here, all the way to 2 pi is going to be probably like this. So this and that, orange and blue, exactly the same thing, isn't it?
Doesn't the orange line go all the way up to 1 on the right side of the
This
graph?
side, all the way to theta equal to pi to 2 pi.
Yes, but your line in the graph at the
Pi.
bottom does not go back to 1. It starts at,
Okay,
yeah,
right here.
yes.
That's right. So this is 2 pi.
Yeah.
You're right. Question, go ahead.
Your CP, like, how do you get CP equals 1 and -3? Is that from that graph?
This is -3.
That's, oh, okay. It's just not-
This is 1. Okay. All right. So this is upper side, lower side. You can get any value of CP. Now, you're going to pick up CP equal to 0 location. Right here, okay? CP equal to 0 right here, right here, right here, right here. Multiple locations. However, CP equal to 0, the meaningful locations here and here. Forward surface, okay? So let's find out that angle. this angle. Do you think it's 45?
Did you
No.
say it was
No.
like
I
30?
feel like it's 30.
30. Is it 30? Let's find out, okay? So again, if you take a cross look at surface pressure distributions, you can basically tell the pressure distribution upper and lower surface, forward and backward surface are completely symmetric. So it's impossible to create a drift or drag, okay? So this is called non-lifting flow over the circular cylinder, the Allenbut's paradox. Because people don't believe you saying, well, this flow doesn't create even drag. Huh? Why is that? Because we are completely ignoring some physical phenomena, physics out of it. This is ideal flow. So ideal flow, basically you include all of those assumptions such as viscosity is 0, density is constant, this is steady flow, and zero gravity, and even irrotational, mathematical sense. So from that assumption, this is the solution. And then is this completely wrong solution? No. It's just that basically do not include some of the physics that actually produce the drag. So if you understand that physics, you can compute that physics in a separate system or separate kind of software, attach that result onto this result, then you can actually reproduce something more meaningful, real flow field. That's the approach of aerodynamics theory. Without theory, you cannot predict anything, right? So some kind of prediction is a baseline solution, but the baseline solution oftentimes ignores some of the physics. So in this flow regime, you can no longer assume density is constant. That means more than 0.3 Mach number. Okay, so let's just compute the density as a variable. And then let's just superimpose that result into this original baseline assumption, original baseline solution. That is going to produce a simulation of high-speed flow. Of course, if the flow is really high speed, you can continue ignoring viscosity, of course. That's error 2. You know, if you start taking error 2 and start talking about supersonic flow field and then formation shock wave, you can ask this question to the professor saying, hey, what is the Reynolds number for this Mach number 2.5 flow? And then professor is going to be like, what are you talking about? Of course, viscosity is 0. I don't even talk about viscosity. This is high speed flow. What are you talking about? That's a response. Because high speed, okay, what is the dominant physics? That's a compressibility, formation shock wave. That is almost all the drag source of it. Viscosity, of course, yeah, contribute a little bit, but who cares? Low speed, okay, go right into the low speed wind tunnel and then pick up one of the sharp senior student, ask this question. What's the Mach number of this what's the Mach number of this wind tunnel? Then that senior student look at you and then react like, oh my goodness, I have another idea. But, yeah, I don't care. Ask me instead Reynolds number or something. Otherwise, I'm going to treat you like a complete idiot. You're not welcome in this place called low speed wind tunnel. Because physics of Mach number, which is density, what do you think? Density changes? Yeah, but how much percent? Less than 5%. Who cares about that? And there's no way we can keep track of that kind of stuff, right? So that is aerodynamics. If you don't know the concept, you are probably treated as an idiot in your workplace. Okay, you are not even one that we can communicate or have a discussion of anything, of aero, because you don't know a damn thing. So please avoid that. That's everything for aero. Okay. So anyways, question? Go ahead.
Can you scroll up a little bit on that diagram?
Yeah.
How come you have V infinity coming in, but 2 V infinity coming out of the top and bottom?
You can compute that using math. You did it, actually, by the way. Didn't you do that? Look at this. Suppose plug in sine equal to half pi. It's going to be 1, right? Minus 2 times b. Okay, that's what you get. Well, actually, minus sine pi, what's that? Minus 1, is it? Something like that. So you get 2 times b infinity sine, 2 times b infinity. Use this equation, you can determine the velocity on the surface. Mathematical solution, you get it. Okay? Anything else? You can determine any velocity at any location. It's a function of theta, right? It's 100% mass. That's what we are doing. Any other question? Okay, good. So this is the question, okay? This is the question. So now, consider the flow over a cylinder over the surface of the cylinder and calculate the locations where the surface pressure static becomes equal to the free stream static. Ooh, what kind of location is that? What kind of location do we call? If we make a drill hole, what kind of location? This is static pole. It's not, it has nothing to do with statics class, okay? Please. P go to P infinity. So surface pressure P, actually Cp, is a function of theta. We know Cp is 1 minus 4 sine square theta. Is right? Is that right? Cp as original definition, P minus P infinity over Q infinity, isn't it? Right?
Yes.
Okay. So if P becomes P infinity, Cp equal to 0. Cp equal to 0 here. Cp equal to 0 here. Now this is the other side of the flow field. So this is forward surface, backward surface. These locations, yeah, mathematically you can find it, but realistically we cannot use it. Right? We can only use the forward surface. So let's just find out. Okay. So stagnation point, what is the Cp? Stagnation point. Cp is 1. How come is that? How come it's, well, Cp is equal to P minus P infinity over Q infinity. Where stagnation point is B infinity is equal to 0.
Yeah.
Then Cp is, how come Cp is 1?
We have,
Well,
isn't Cp is equal to 1 minus V over V infinity squared?
yeah. So what happens to pressure P at the stagnation point?
It's equal to pressure.
P becomes P0. Okay? So P0 minus P infinity divided by Q infinity. Okay? So if you plug that in, what's P0 by the way? P0 is 0. What do you mean? P0 is a total pressure. What makes total pressure?
P infinity plus Q infinity.
Total pressure is P infinity plus Q infinity. That's right. Subtract P infinity divided by Q infinity. What is it? 1. Because this becomes Q infinity over Q infinity. It's 1. So at the stagnation point, Cp is 1. Obviously, this is the highest possible Cp value you can have in the flow field. Okay? And then static pole. Go ahead.
Where you have, it says V infinity equals 0, do you just mean V, not V infinity?
Yeah, you can say, yeah, you can say that. Because you want to talk about B over the surface.
Yeah.
Oh, okay. B infinities cannot be 0. Yeah, that's right. Good point. I appreciate it. So that's right. So velocity becomes 0, then pressure becomes total pressure. Total pressure is static pressure plus dynamic pressure of the free stream. Okay. I appreciate that. Now, static port. Okay. Static port is the location. Pressure becomes P infinity. Okay. So then, if you compute Cp, Cp is going to be P infinity minus P infinity over Q infinity. So this is 0. So if you want to find out the theta corresponding to it, we do know Cp is equal to 1 minus 4 times sine squared theta. Let's set equal to 0. So this is going to give you sine theta is plus and minus 1/2. This is going to give you theta as a multiple solutions, right? 30 degrees, 150 degrees, 210 degrees, 330 degrees. Which one do you think you choose?
150, 210.
That's right, those two. Those two are forward surface. Okay. So that's the location. So 150 and 210 literally means that this angle here is 30 degrees up from the center, 30 degrees down from the center, because this is measured from here, 150 degrees, and then this thing is 210 degrees. Okay. So those are the two meaningful locations of the static boat. Okay. And then what is the CP corresponding to? Okay. Also note. Yeah, CP is 0. Also note. Okay. CP at the minimum, CP at P min or B max location. Okay. So let's find out. Okay, so the location where the CP becomes lowest or velocity becomes highest. So this is a minimum pressure location or maximum velocity. Also here is minimum pressure or maximum velocity. What is that? Angle-wise, theta equal to half pi, right? So you can plug in CP at that location. CP is equal to 1 minus 4 times sine square. Theta equal to half pi. This is going to give you minus 3. Okay. So CP at pressure minimum or velocity maximum point is minus 3. Obviously, if you plug in sine half pi into the velocity equation over the surface, it's going to be 2 times V infinity. Okay, magnitude. So, of course, B max is equal to 2 times V infinity. Again, you know the location of theta. Theta is half pi, or minus half pi, or 3 over 2 pi, either way. Okay? Any question? This is a very simple math, and then I wanted to show you one thing. Okay, one thing you probably forgot about, but I have a picture here, just a straight application of this fact, in which here. I don't know if I showed you or not. Yeah, this is the directional finding pilostatic. So now you know the angle from the center, right? This is 30 degrees up, 30 degrees down, 30 degrees up, left and right. So if you make a drill hole with a 30 degrees of angle apart over the floor of the sphere, this is going to create a static force. This is the center to this stagnation point, right?
And that's only if your static port is cylindrical or spherical.
This is spherical, like I said. Perfect sphere, half sphere. Of course, yeah, because this is essentially direct application of flow over the circular cylinder. Yeah, the project you're working on right now. Okay. Question here. Go ahead.
How do you get the Vmax?
Okay.
How did you get the Vmax?
Well, like I said, this is third time saying it. Okay. This is the equation you know already. Plug in theta equal to half pi. You get the B max 2 times B infinity, right? Okay, any other question? So if you take a look at and compare the ideal versus real flow field, okay? So let's just for a moment start taking the theta from the stagnation point forward surface. So right here, you are going to start from stagnation point forward surface right here. CP equal to, of course, 1, okay? Then as you move along the surface right here, pressure drops, and go across the 0. In other words, this is the static pole. And then go all the way to the 90 degrees minimum pressure point, CP equal to minus 3. or maximum velocity point, minimum pressure point right here. And then if you go beyond that, pressure actually start decreasing, increasing, and increasing. Go back into Cp equal to 1, another stagnation point here, flow away. I'm just looking at the upper surface right here. Okay. Now, this is the ideal flow solution in which 100% mathematics. Let's compare against the real thing. Okay. Does that actually represent some of the physics of the real flow field? Yes, it does. So the real flow gets in here. Then once again, Cp is also 1. Okay. Then as you move along the top surface, of course, you know, you're going to decrease the pressure, and pressure, and pressure. And then, of course, creating minimum pressure point right here. But right after that, pressure all of a sudden starts decreasing, well, it starts increasing. In other words, advanced pressure gradient, it's probably today's freshman student. I cannot take any advanced pressure. But that's it. I quit. I have no tolerance of any uncomfortable situation. I just quit. I hope, well, you're not one of those because you survived all the way to here. Okay, that means, oh, you have some resistance against that kind of stuff. But this is separation. Flow separates. Flow separation, big time. Okay, go ahead.
Is CP just like undefined after the flow separates?
You can actually still measure the Cp on the surface if you have a pressure tap on the surface.
Okay.
It actually gives you a value. And then those values will probably respond back to this kind of value, right? Even though the flow is completely separated, but on the surface pressure, you can still measure by, you know, pressing the static pressure taps and then manometer connected to it. Okay, so flow separation actually creates the temporary relief effect. That means the pressure goes down quite a bit. So you're going to actually release the high, supposed to be high pressure, but those high pressure will be all gone, separated. Temporary release. That means you have a low pressure zone here. You create the low pressure zone. And then overall effect is the force created in opposite direction to the motion of the body. You know what I'm talking about? This is a drag. And then this drag is the force created because of the pressure difference. You're actually creating low pressure zone by flow separation. As a result, the force is created because of the pressure difference. This is called pressure drag. Drag due to flow separation. If the airplane is pitching up really, really high, you're going to induce the flow separation here, creating huge drag, and airplane cannot sustain the flight. What do you call that kind of situation? It's called the stall. Airplane stall. Flow separation causes airplane stall. This is separation drag. Pressure drag or drag due to flow separation. Go ahead.
There's the reason there's that little bump in your pressure coefficient. Is that because the vortices turn into the middle?
That's probably circulation, lots of things going on here.
Yeah.
Flow separates, circulates.
But because of the circulation where it hits at theta equals 0 or 180,
Probably.
is that where you get that little lift?
Probably. I mean, we shouldn't explain that kind of simple method because flow is very turbulent, very random. Flow separates, creating wake. Wake is very random, chaotic flow. You cannot simplify it just like that, but that's one of those reasons. Okay, so this is the real flow field. At least we can represent actual flow field until it actually separates. Because the ideal flow cannot simulate any flow separation because we completely ignore that, right? What causes the flow to separate? It's the boundary layer. Viscosity needs to be in place. And the viscosity's characteristics, either laminar flow and then turbulent flow, what causes the transition from laminar to turbulent needs to also properly analyzed. Otherwise, you can never, represent that kind of stuff. It's not simple. That's the bottom line. But you can do analysis in separate software or something. Go ahead.
That drag caused by the separation, that's only a component of the actual drag because we're still ignoring the viscous effects, right?
This is a real flow. We are not ignoring anything.
Okay.
Okay. So we are not ignoring anything, but this is a flow separation we are showing. Now, flow separation creates the drag. That's called pressure drag. Also, another drag is even though the flow is attached here, it is going to cause the friction because the viscosity is also included. So that is also completely ignored here. Right? So two different kinds of drag we completely ignore. One is skin friction drag. Even if the boundary layer stay attached on the surface, it is going to cause the friction, tau equal to mu du dy. Okay. The other one is, of course, I talked about pressure drag, flow separates, that actually create much larger amount of drag than skin friction drag. So those two combined together is going to be total drag, CD. CD is equal to CDF plus CDP. Actually, we should say CD is equal to CDF plus CDP. Okay. This is a 2D airfoil, something called drag polar. This is aircraft wing, or it could be aircraft itself. 3D drag polar. Drag polar is something you have to figure it out when you start taking flight mechanics. What is the drag polar? That's quite important because that is going to determine your aircraft's performance. How much you can continue flying, how much you can climb up. Everything depends on this drag polar. Okay, so drag polar is an important term. You have to figure out. One of the tools available will be Xfire 5. It's going to compute you the drag polar. And then one of the tools, wind tunnel, you have to compute drag polar. Xfire 5 is, of course, theoretical method. Wind tunnel, of course, you can do that. Or CFD. Oh my goodness, this is challenging, but you can still do it. This is flight mechanics, wind tunnel testing class you're going to take. This is CFD. If you want to take it, I can create one for you. So anyways, drag polar is something you have to figure it out. Consists of two different kinds of drags added together. Okay. So real flow, if you take a cross look at real flow field. This is the actual data. This is a capital CD. This is drag coefficient of the sphere. Okay. So if you do a testing of the drag coefficient of the sphere and then plot it over the range of Reynolds number, take a look at this is log scale. So it's like a really, really low Reynolds number to the fairly high Reynolds number, and then there is a dip. What is this? What do you think this is? Anyways, let's take a look at it. Okay. So very, very low Reynolds number. Obviously, almost all drag is skin friction because flow separation doesn't happen. Okay, skin friction only. So there's no separation or pressure drag. So that is really low Reynolds number, sometimes called creep flow. Have you ever seen like a physics festival or something? You know, somebody actually show you, oh, this is a demo. This is very viscous fluid. This is a steel ball. You drop it into the very viscous fluid, and it's going to go slowly goes down. That's what it is. 5 more minutes. Skin friction only, no flow separation. Now, right around this Reynolds number range, of course, you are going to start seeing the flow separation here. This is very interesting flow separation. Flow separates, however, create the separation bubble and reattach here and keep circulating. This is a separation region, but the separation region stay attached on the surface. This is called separation bubble. Okay. Two bubbles form the separation bubble. And then if you increase the Reynolds number more, those two separation bubbles start to separate from the surface, alternatively shedding the vortices. It's called von Karman vortex shedding. Someone's name. Von Karman shedding of vortex. That's in this range of Reynolds number. Now, if you increase the Reynolds number, of course, this shitting becomes much more random and then chaotic. This is something called subcritical flow separation. And then something happens right here, burn dip. This is supercritical flow separation. What are those differences? Question?
Does that major drop that occurs, is that due
It
to
actually
the
occurs,
stall?
yes. Eh?
What?
What?
Is it due to a stall?
No, this is flow over sphere.
Yeah.
So again, this range of Reynolds number naturally transition the flow from laminar to turbulent, actually. So that's next page. So this is the this is called Stokes flow, very creepy flow, Stokes flow. Stokes flow, the other one is von Karman. This is von Karman, this is a separation bubble. Okay. Stokes flow or creep flow.
Oh.
Creep flow, either way. So everything is given here. But so those are the drag coefficient. And then here is the two things. One is the subcritical flow, the other is supercritical flow. Now, subcritical flow is the flow separates right here at early stage because the flow is laminar. So laminar boundary layer separates at early stage right here whenever the adverse pressure gradient starts happen. Flow separates all of a sudden, creating huge wave lesion. Now, if you increase the Reynolds number, this laminar turbulent, laminar boundary layer transition to laminar flow to turbulent, okay? Turbulent flow stay attached on the surface a little bit more. So delays the flow separation. That is going to cause the dip of the drag coefficient, okay? And then overall, drag coefficient decreases here. One is subcritical, supercritical. Have you ever seen golf ball?
Yeah.
That's what it is. Golf ball dimples, the purpose is intentionally trying to transition laminar flow to turbulent so that it is going to stay attached more on the surface, delaying the flow separation. So it's going to go fly more distance. Right?
Is that what the vortex generators on some wings are?
That's right. That's also true. You intentionally create the turbulent flow by putting the vortex generator on the surface. And then, of course, it's going to increase the skin friction drag, but it is going to minimize the flow separation, minimizing pressure drag. Sometimes you have to do that. Honda Jet actually have to do that. There's a guy actually got a job at the Honda Jet after this person graduated. And this person was working with vortex generator of the Honda Jet. He said, it looks horrible. But again, we have to do that. It looks horrible. Vortex generator, just like this. Look at that. Vortex generator. Oh my goodness, why do you need to do this kind of thing? Because you want to transition from laminar to turbulent to avoid the flow separation. And then people say, well, it's going to increase the drag. Yeah, skin friction, yes, but the separation, no. Especially for high angle attack maneuvers. Okay. So it's always trade-off. Any questions? So again, next week, go ahead.
Isn't that called tripping the flow? If I'm remembering this correctly?
Tripping the flow is also, it's a transition from laminar to turbulent in the wind tunnel testing. Yes.
Okay.
Trip wire, same thing.
Yeah.
You're going to force transition from laminar to turbulent, yes.
Okay.
Right. Good point. So again, this concludes the Unit B3. However, on Monday's exam, Unit B3 is not going to be included. I'm going to announce when is going to be the B3 homework is due. Don't worry anything about until you complete Monday's exam. On Monday, right after the exam, you're going to hear, okay, so this is homework due.
I have a question.
Go ahead.
I was concerned about the projects for part 2.
Yeah.
Do you want us to allow you to input the stagnation point, or do you want it to?
You have to input the stagnation.
So
I showed you my code.
yeah, so we don't do it. I mean, you don't do it as the user, but we.
I
have
do
to
as a user.
default.
I typed in stagnation treatment type. I showed you. So you should probably do that.
No.
Yeah, I'm saying that
Yeah.
the user will have to input the 0, right?
I did, yeah.
Okay.
That's what I did.
And is default, having defaults as the set numbers,
Yeah.
is that okay?
Oh, that's one of the techniques you can do in MATLAB code.
Okay.
Yeah, you can do that. Do you know how to do it?
Yeah,
Empty input
yeah.
is automatically taken as something.
Okay.
Yeah, it's a condition. Any other question?
Okay.
All right, have a great weekend, and we're gonna see you back on Monday for midterm exam 2. Good luck.
Yeah.